All right, you guys, this is the last of the related weights problems that we need to wrap up. This is just another example that is very similar to the angular measurement problem we just saw in example number 4. So this example says, an observer watches a rocket launch from a distance of 2 kilometers. The angle of elevation, theta, is increasing at 3 degrees per second at the instant when theta equals 45 degrees. How fast is the rocket climbing at that instant? So you can imagine that there is a person who is watching a rocket launch, maybe at Cape Canaveral, or maybe some kind of satellite rocket launch at Vandenberg Air Force Base. So they're watching from a distance of 2 kilometers. So that's an x value, and that's going to stay constant. So this person isn't moving, the rocket is moving, and so their angle of elevation is changing. So if we imagine a rocket being launched off here, give it some flames, this is going to be our y distance. And then we are interested in how the angle of elevation for the observer is changing. So that's going to be this angle measurement, theta. So as the rocket is increasing upwards, that angle is also going to increase. So what we need to think of is what is the information that we have, and then what are we solving for? So this tells us that we have theta. Theta is 45 degrees. And it gives us how theta is changing. So it tells us that d theta dt is equal to 3 degrees per second. So then it asks us how fast is the rocket climbing. So if it's asking us how fast the rocket is climbing, what it's asking us to solve for is dy dt. So this problem setup is going to be very similar to what we saw before. The only difference is that instead of solving for d theta dt, we are given d theta dt. So same trig function as before because we have both the opposite side and the adjacent side. In this case, our x value is what stays constant at 2, so we just get to substitute that in. Once we have a relationship that equates information about theta to information about y, that's when we can start differentiating. So this guy will become secant squared of theta, and then we need to acknowledge that we're differentiating with respect to time. So d theta dt is equal to, remember this is really 1/2, so we can just say 1/2, and then we multiply that by our dy dt there. At this point, we have a theta value and we have a d theta value, or d theta dt. So we're good to go to solve for dy dt. The only thing that we need to catch before we start plugging things in is that all of the information for us here was given in degrees, and we want to be working in radians. So this 45 degrees, we need to change to pi over 4. That one's pretty easy to think through, but this d theta dt over here, we're going to have to multiply by pi over 180 in order to get it into radians. And so if we simplify this fraction, that's going to be pi over 60. So we want to simplify that before we plug in. So now for secant squared of theta, so secant of pi over 4, we're going to take that quantity and square it, and then we'll multiply that by d theta dt, which is pi over 60, and that's equal to 1/2 multiplied by dy dt. So if we think about pi over 4, if you just kind of want to give yourself a nice little unit circle to think about, at pi over 4, our sine and cosine value are both root 2 over 2, and so secant is going to be the reciprocal of cosine, so we can just take that root 2 over 2 and we can flip it upside down. So this will become 2 over root 2, that quantity squared. That's what we're going to multiply by pi over 60, and that's going to be equal to 1/2 dy dt. So if we square this guy, this will become 4. The bottom part will become 2, so 4 over 2. That means we're going to have 2 pi over 60 equal to 1/2 dy dt. And so our last step is going to be to multiply both sides by 2, so I can get rid of this 1/2. So I'll end up with 2 times 2, so 4 pi over 60, which is the same thing as pi over 15. Now, because we're working with an application problem, we want to go ahead and round that value and see what that's equal to. So let's go ahead and plug that into our calculator, pi over 15. And so when I do that, I get a dy dt value of 0.209, and we're dealing in kilometers per second, so that's going to be what our value is reported in.